Hi, everyone, and welcome to our webinar today. My name is Paul Bemis, and I'm here with my friend Henry Amistadi. Hello, Henry.
Hello.
We're going to spend some time today talking about some work we've been doing in the area of simulating energy in the data center. Henry's led a lot of this effort and is my resident expert on this topic. Henry and I have known each other for quite a few years. He was a data center manager at the MITRE Corporation in Bedford, Massachusetts when I first met him, but has a long history in the area of energy modeling, and we got along very well early on this topic and talked a lot about it. Subsequently, he has retired and semi-retired, I would say, Henry. And, he's living in Vermont, and we're co-located pretty close to one another, so we've been collaborating on this topic. Henry is an expert, as I mentioned. He's also involved with the TC 90.4 committee and also 9.9, pretty heavily involved with ASHRAE, as am I. I am an ASHRAE member and also president-elect of my local chapter. And this issue of simulating energy is important, I think, to both of us, and I think it's going to become more important to people in the industry over time. Just a couple of housekeeping things for today. This is a webinar. We are recording it, and I have everyone muted except for Henry and I. However, I do like to make these interactive. As a result, you can ask questions. I prefer that you type them in as opposed to opening mics, which causes all kinds of feedback issues. So there is a place over on the right with your GoToMeeting interface that popped up, and there's a place to ask questions. I have two monitors up, and I will look at the questions and try to handle them as we go. Some of them I'll take, some of them Henry will take, and I'll direct that. So please ask questions as we go, and we'll try to do that way. Okay. So I want to just do a level set first. The audience is fairly diverse here, so I'm going to just back up and do a level set. PUE, I've done a lot of this before. I try not to be repetitive, so please bear with me. Power utilization effectiveness. It is total facility energy divided by IT energy. It was originally intended to be a representation of how effectively the IT is being cooled, how effective the facility is at cooling that IT equipment. It is made up of total facility power is made up of all the power, including cooling plus IT. That's the numerator. The denominator is just IT power. But this particular metric has come under some criticism lately, and we think rightly so. Both Henry and I agree on this. PUE has some issues. For one, it's very difficult to measure. That is, the IT load itself doesn't stay constant. So trying to figure out what your IT load is difficult. You have to do this, by the way, for a whole year. PUE should be an annual number, not an instantaneous number. Furthermore, it does not take into account environment. So, you know, a data center in Alaska is not the same as a data center in Florida, even though they may be exactly the same with respect to mechanical unload and everything else. The PUE number is going to be different. So why penalize the person in in Florida for the person in Alaska? So that's part of it. It doesn't take into account environment, geography, as I mentioned. It also is dominated by IT load. I mean, if your cooling system is very efficient, then this turns into a ratio of IT load to IT load. It's really dominated by that. And so it's difficult to use it as a way to show improvements in cooling efficiency. And therefore it can be gamed. I think this is the biggest criticism of it. I continue to go to these conferences and I hear people tell me that their PUE is 1.1, and I just scratch my head and think, what are we measuring? What does that mean? Is that, where are we? Is it in Florida? Is it in North Pole? If it's the North Pole, just open the window, you've got a PUE of 1.0. So a lot of times these end up being spot measurements. There's no criteria really to it. The system for measuring it is poor. So it's not a great metric for indicating energy efficiency in a data center. Now, ASHRAE has recognized this and been doing some work on this. And if you look at PUE, it really turns into, assuming your UPSs are efficient and everything else is efficient, and which are becoming more efficient, it really turns into cooling power. That's the dominant parameter in that numerator, cooling power. And then you have IT energy and IT energy. So if you focus on the cooling efficiency, if you focus on these two, and I've presented this in earlier webinars that I've provided, where I've focused really on the ratio of these two things. And that's exactly what ASHRAE 90.4 did. Now, they actually did an inverse of this. It's actually IT energy over cooling power. It's 1 over this. But nonetheless, it is a ratio of these two elements. And the 90.4, it's called a mechanical load component. And it is the ratio of these two parameters. So now we're getting a good look at, now this is very much like when you see a chiller efficiency, which typically is measured in kilowatts per ton, which is a crazy series of numbers because they're not unitless. But it's the same idea, except it's for the entire system. It is the amount of energy that we're using to cool the data center, including everything. So if you look at 90.4, it's a minimum energy efficiency requirement for data centers. It applies to new data centers as well as existing data centers. It applies to modifications to data centers. It references 90.1 for all building envelope specifications. 90.4 was an extension to 90.1 because we realized, ASHRAE realized, that there were data centers in some of these buildings. How do you handle LEED certification on a building that's got a data center in it? That was the fundamental question. And it's based on annual use. And there's a new definition in 90.4, which is mechanical load component. It's an annualized component calculated, and most recently, in the most recent spec, in 4 sections, based on 19 climate zones. And it also has specific ITE criteria as well. That's the IT side. And they use 4 points. They use it's mechanical power divided by IT power, effectively, at 4 different points. So now not only are you taking a look at the ratio of, really, this is really an inverse of COP. It's a COP number. It's upside down. But the point is it's ratioing the mechanical power to cool compared to what it's trying to cool, the IT power, at 4 points. The reason for the 4 points is to understand how that cooling system behaves itself at low IT loads. This is something that often happens. You design the cooling system for a data center to match worst case conditions, and then you never load it to worst case conditions, and so it never runs right. The cooling efficiency is never high because everything is way off its design specification. So this was an attempt to try to put some better fundamentals in place and better metrics in place. And here we're talking about the mechanical power being the sum of everything. So it's really a systems level coefficient performance kind of ratio. It includes cooling pumps, heat rejection fans, air handlers, etc. So we think this makes a lot of sense. And of course, now there's criteria that you can meet. And it ends up, as I mentioned, being essentially the inverse of COP for the entire data center operation, which is a good thing. So opportunity for energy modeling now becomes apparent. Now that we have a standard set or specification set for this, the opportunity to create an energy model for the entire data center exists. This is something that I've wanted to do for quite some time. We've added, as you probably know, if you're a CoolSim user, we have energy metrics in there, but you had to, up until this point, do hand calcs to do it. But now that we have this, you can do modeling. You can actually model the cooling system and measure its performance against the criteria that has been set in place by ASHRAE. And it is geographically based on climate zone. And you can develop system level models for each of the components, and that's what we've been working on. So efficiency adjustments for things like fans, chillers, pumps, cooling towers, all of these things have an empirical curve of efficiency, energy efficiency, that is a function of load. The analogy I'll use here is your automobile. You know, the automobile engine it runs most efficiently at a certain RPM. The transmission is a way to get you to that RPM. That's why they have a transmission. It doesn't work well at low RPM. It doesn't work well at high RPM. It's made for something right in the middle. And you'll even notice in the automobiles today, they're getting more gears. Now they're up to 8, trying to keep that RPM constant. Same case here. Whenever you move off the design center of a fan or a chiller or a pump or a cooling tower, energy efficiency will drop. So keep this in mind in the design side, because you're trying to design for worst case, typically max load conditions, but how does it behave at part load? What's the part load ratio? How does it behave when it's not on the center of that design center? The other part here is coupling it with CFD. This is the first time this has ever been done commercially. When I was at Fluent, we did it for other processes. We did it in the chemical process industry. We would do it for heat exchangers. Here, what we're doing is taking CFD output from CoolSim and feeding it to the energy model so that we have a coupled system that allows you to model the entire environment. So we take output from CFD and feed it to the energy model. This gives you now a full tool for understanding how to improve the energy efficiency of the whole environment. It'll even allow you to do things like change the location of the data center. What if we were to take a given data center and put it in Oregon versus Florida? Should we use an evaporative system versus a air-cooled chiller? These kinds of decisions can now be calculated, can now be modeled. Things like changes in control strategies can be done. What if scenarios? What if I lose something? What if a chiller goes down? What if the second data center or the room that I'm putting on this plant is not going to come up for a period of time? This helps you in the decision-making process because it allows you to understand the implications of those things. And also, I think this is going to become rather important: compliance. Is it compliant to 90.4? We see LEED certified becoming a fairly well-recognized moniker that people are encouraged to pursue. We think that this will be the same way. 90.4 will become something that data centers need to adhere to with respect to efficiency. And really the best way to know whether you've done that or not is to build a model of it and see if it does. So we're developing this modeling. Henry has certainly led this effort, been a big part of what we're doing here, and we will include these metrics in the output of the software. So what we're going to do today is walk through an example of how you would use this and how it ends up looking. And I'm going to show you some of the early work we're doing with respect to the output that's coming out of the system as a result of this work. So the first thing we'll do, and I've done this in many other webinars, and so I'm not going to do it all here. I'm trying not to be redundant. If any of you want to know more details about how to do some of these things, just send me a note and I'll refer you back. I have the recordings of all the webinars we've done in the past on our website, and furthermore, this one will be recorded as well if you want to go over it again. So the first thing we need to do is optimize white space. This is generally airflow management techniques inside the data center itself. And then we optimize the mechanical system. We're not going to do a lot of this today in the interest of time, but there's a lot of opportunity. What we're finding, what Henry and I are finding as we go through examples and we start to do work in this area, is that the opportunity to optimize the mechanical system is fairly dominant. Right, Henry? I mean, we're seeing the mechanical side efficiencies can save a lot of money. So things like pumps, coolers, chillers, and then use modeling techniques to determine what the upside potential is. For example, what's the simple break even? What's the crossover point before you earn your money back? It's usually the one that drives it. Although carbon reduction is becoming a big deal too. How much carbon can we reduce from doing these things, carbon emission? And it can predict that quite accurately. So we're going to show you how to do this today in a very simple example. Again, today what we're trying to illustrate to you is primarily methodology. We're trying to just show you what the sequence would be. Again, this has been reviewed earlier. I don't want to belabor it. First step is model the existing conditions with a baseline. Step 2, drop the total air supply by the air handlers to match the demands of the racks. For those of you who have been through DCEP training, this is should be very natural to you. DCEP is a data center energy practitioner training delivered by the Department of Energy. This should be very obvious to you. I'm going to use terms like RTI. RTI is the room thermal index or temperature index. It is a ratio of the amount of air the racks need compared to, as a ratio, to the air handler delivery. So the air handler delivery flow is usually too high in most data centers I visit. So this number will be lower than 100 because it's rack demand is in the numerator. And so VFDs are popular to try to get that to closer to 100. The next step you do is to drive the supply air temperature up as high as possible until the RCI high, which is the metric. Again, I'm referring back to DCEP training. RCI is the rack temperature index, and it is hot spots on the rack inlets. The TC 9.9 thermal guidelines suggest you shouldn't be higher than 80.4 Fahrenheit. Sorry for my SI guys, it's 80.4 Fahrenheit on rack inlet. And RCI just calculates how many of those areas you have. You want it to be in the high 90s if you can get it there. A few hotspots don't matter because you don't put equipment everywhere in the rack, but you certainly want it to be above 90. Typically take some air management techniques to get you there. And that's it. That's what you do. That's the optimization routine, and we've done that before in earlier webinars. So today we're going to use two arbitrary rooms that I picked from a pile of models that I've had over the years. Pretty common ones. These are chilled water. We're going to use a simple air-cooled chiller here for these two rooms. The room on the left is 6,000 square foot. It's got 31 racks, about 623 kW. Over here on the right, this one is a little bit funky. You know, you'll recognize this because it's got crazy walls and it's got partially filled cabinets. This one's a little under 10,000 square feet, 71 racks, 235 kW. So we're looking at a total here of about 858, a little under a megawatt of power going into these rooms. This is a diagram of the layout we're going to use. We're going to be using air-cooled chillers on this one. The air-cooled chillers are becoming popular in many places. I see a lot of them in Europe. So this would be like an Airedale chiller. And you see there's an economizer loop here. You can go by the chiller if the temperature allows you to bypass the chiller. Over here are the loads. These are the rooms. So and here we have outside air coming into these heat exchangers on either side. So outside air comes in and out of the heat exchanger here on the air-cooled chiller. These are usually very large and make up most of the space of the unit itself. They usually sit on the roof, and they're quite large in terms of physical size. And then the rooms are over here. So there's my room 1 and room 2. This is just a fan coil representation here. These are fan coils in the room. That's how they work, and they are generally either, well, the older style used to be constant speed, more recently are VFDs. So here's your primary loop here. Pump drives the fluid around to primary loop, and then you have a secondary loop with a pump that drives here, and you use valves to allow the fluid to enter the rooms, and that controls the pressure deltas. There's pressure sensors that operate this. This is a fairly straightforward, common representation of how the system is done. 2 chillers are there for N+1, typically 2 pumps. Everything is got doubles on it for redundancy. Room 1 here, pretty straightforward. I already mentioned to you, we assume the air handlers are running full tilt because that's not unusual for older systems. Total rack demand 114. You see that ratio right there is off. The racks want 114, we're delivering 160. So we've got too much air coming through the air handlers compared to what the racks want. This tends to make the return air temperatures too cold, hurts the heat exchangers, hurts the chillers, drives efficiency down. Air supply temp, 60 degrees, usually, often I see that, it's too cold. So therefore my RTI is below 100. You can see RCI high is fine. RCI low is 22, it's too cold. This picture over here represents that. This is a conformance plot that comes out of CoolSim, and you see here that the temperature is 80.6 on the high side. This green is the conformance zone. That is to say that if you're green, you're good. It's kind of like a reference there, and blue means you're too cold. If you saw any red, it means you're too hot. These are rack inlet plots, and you can see we're seeing an awful lot of blue there, which means we're wasting energy. Oh, there's a link here to CFD output. Most of you have seen this already. I don't want to belabor it, but I will show you that there's a whole bunch of output that comes out of here in 3D form. And I'll show you some of the issues associated with this particular representation. So I'm going to show you path lines from tiles here. There's a couple things about this data center that are a mess. This is a 3D representation of the air coming out of the tiles. This is what comes out of the CFD modeler. And you see an awful lot of recirculation going on right here. So right here, the air is coming up and back into the heat exchangers. Now this is a bad thing because we're cooling off those returns. You shouldn't see those at all here. This is only supply air. Only the air coming out of these perforated tiles is what should be seen. It should come up and stop right in front of the rack, and it doesn't. It comes up and it blows by. There's too much of it. And you see the temperatures dropping here as we get to the return. So it's cooling. It's actually increasing, right? It's this cold air is being warmed by the room, really by the output of these racks here. Furthermore, we've got problems over here. We're a little too close. In CoolSim, you have this nice ability to remove some of the surfaces so that you can see. And I'm just going to turn off my racks here so that you can see what's going on behind. And you see right there the Bernoulli effect happening. So you've got very high-speed air coming down under the floor, coming along from that crack unit and bending. So these racks are starving at the top for cool air because the air, due to momentum, is going that way. So that's a good illustration of putting your racks too close to your cooling units. So there's a bunch of these plots. I thought I would show you at least that one to show you what's going on with this particular design. Not a good design, but not unusual. It's not unusual that I go into data centers and see things that are set up that way. The next one is, equally problematic. It's probably grown over time. The racks have holes in them. I won't show you that for interest of time, but well, similar thing here. You've got air going everywhere. The RTI here is 50%. So let me show you the same plot just very quickly. This is the plot of air coming out of the tiles. Same problem, air going everywhere. So this is kind of a mess. You can always tell and remember that it's not supposed to be doing that. You're not supposed to see these path lines go anywhere but straight in. This one's also unblanked, if you notice. And let's turn off that block so that we can see through the wall there. But you see there's holes in those racks. They didn't blank. So that's also a problem. So that one's got way too much air, and it's not in great shape either. Now, what we've added to this is the ability to see the energy report. So here's an energy report that we're building. It popped up on my other display. And now we have energy. We did this run for Boston, Logan, which probably isn't the great place to do an air-cooled chiller, I noticed, Henry. And then we do performance for the plant. So here is energy for the overall use, kilowatt hours, monthly averages, average hourly PUE, average COP, MLC, and annual cost to operate. So it's costing about $110,000 to operate. Over here are all of a various set of plots. For example, dry bulb as a function of time. So there's the entire year. So here we're doing calculations for every hour of the year. For each hour, we calculate the energy consumed by the cooling system. We do that by summing all of the energy loads and the cooling loads. We do cooling calculations. We do cooling capacity readjustments based on return supply temperatures and other parameters. Henry, are there any of these here that you'd like to point out, and specifically on any of these plots that I can bring up just to illustrate them? Or for example, we have power versus dry bulb, energy calculations, overall utilization by month. So here's energy utilization by month. These plots are very nice because you can just scroll over them and they'll give you data. You can also export these plots, download them as a PNG. You can also export them into another program to do work with. And we've put a whole bunch of them in here. This is PUE by month, overall efficiency energy. Here's PUE. Now again, here you can see the PUE values don't change all that much. Again, because the PUE is fairly insensitive to So Henry, is your mic not open or can you not hear me? We seem to have lost Henry. Because there is a question that came in, from what source do you derive the weather data? The weather data, I believe, is TDY data that we procured. It represents all of the ASHRAE representations we need. So we've got, I believe that's what you call it. Okay, so we have all these plots, and also this will all be part of the output report. Chiller pump efficiency here. Here's performance of the pumps. This is their rated power, part load ratios, the cracks. Here is energy performance of each of these. They're labeled crack. It's really an air handler because this is a fan coil in the room. And so all of the data that you could possibly need. Here's chiller efficiency. This is adjustment factor. Every piece of this equipment, as I mentioned, has a curve. And you look at things like part load ratio. How is it being loaded? And then you adjust for it. Okay. So that's room 2. And then room 1, again, I'm not going to go into the CFD detail on this one, but this is optimized now. Now what you see here is a little bit better representation on this particular conformance plot here on the left. I'm sorry, over here on the right. So here we have an RTI of 100, which means we've matched perfectly the amount of air being supplied with the amount of air that is required by the racks. So we're at a 1-to-1 ratio. Now you see a little bit of tearing right there on the edge. Now to do this, we use the containment. So there's your containment sitting there. I just blocked it in so you can see that I put a box effectively around the cold side. So there it is. And the result is that it's in pretty good shape. Now I still have that problem over here, a little bit of falling out, but it's in the high 90s. And the other thing we did here is raise supply air temp to 70 degrees. So we move supply air temp up 10 degrees, which is going to make everything more efficient. Same exact data center, now we've just used air management. So here is room 2, again, used containment. So you can see the containment there, boxed in the cold aisles in this case. That was the easiest thing to do. This one, RTI, I couldn't get RTI quite as high and I couldn't get temperature quite as high because in this particular data center, there's a couple of funky things about it. It's got some side breathing pieces of equipment over here on the right that you'll see that are causing some issues. So let's just take a look at the path lines from racks. I think you can see it there. So these are path lines of air coming out of equipment, and you can see over in this range, we got some side breathers here. So you see these are side to side, very hard to manage these from a containment point of view because they don't breathe normally. You see air is coming out of the back of these devices and from side to side. These are the communication equipment is often like this. So I was not able to contain this section, and that's where you're seeing some of the hot spots. But again, as long as you know that, the issue of containment is sort of one of knowing where your hotspots are going to be and managing them. And so that's how you handle that one. RTI 93, RCI high 90, 99, and you can see over here that problem occurring on those side to sides. Henry, did your mic come back in? I thought so. No, I didn't mute you, Henry. You should be able to. I should be able to hear you. Don't know. We got a few technical difficulties today. So let me take a look at total energy consumptions before and after we did this case. In this one, we are operating at a base case of the total hours at 310, optimized case 248. Overall monthly use, we went from a base case of 226 to a base case of 181. Take a look at the PUE. PUE didn't change that much, 137. we got it to 130. So changed a little bit, but look at the average COP numbers and the MLC numbers. Changed quite a bit. We went 271 to 339. That's one of the reasons why these metrics are better, because we're seeing more of a focus on the mechanical system itself and the ability to get better sensitivity out of that. Total annual cooling power, 371 compared to 275. Total facility power, 109 compared to 100,000. And cost, we saved about $10,000 a year for a Boston location. So about $10,000. We didn't do mechanical optimization here. We simply did white space optimization. What we have found in the work that we've done is that mechanical optimization can gain you a whole bunch of savings. And this is not unusual. This represents about 26% reduction in total cooling power from managing the white space by itself. So that's a fairly good representation. I've got a couple of questions coming in here I'm going to try to handle. Henry, I guess you're not connected. It says your mic's there. It says you're available, but I can't hear you. So you're having some trouble, I guess, with your mic. But let me see if I can handle them. From what source you get the weather? I did that already. What are the energy consumption of components in the data center cooling loop? The energy consumption of the components in the loop itself isn't broken out uniquely. We're doing total cooling energy. But the way we get the energy for each of the components is to take a look at its individual curve. As you can imagine, there's a performance curve for every piece of equipment, and we do it every hour. We take a look at the curve, where we are on the curve, and use its efficiency, what we call part load ratio. What is the efficiency of that device as a function of its design center or design point? So it's a ratio. It's called the part load ratio, and we do it for all devices. Now, devices have different parameters. For example, air-cooled chiller is most sensitive to dry bulb temperature, but again, if you have evaporative cooling or if you have cooling towers, it's going to be sensitive to things like wet bulb and dry bulb. You need them both. So depending on the device, we need different parameters. But this is really just an empirical model. All we're doing is writing the mathematics that represent the curves for each of those equipment, each of the pieces of equipment, and then putting the loads to them that are a result of the data center. And then Henry.
How about now?
Yeah, there he is. Hi, how are you?
Switched over to my headset.
Yeah, nice to have you back. So the question came in about how we're getting these calculations, and so I was just reviewing that. Do you have various chiller manufacturers' data available? Like, do you have the Crack and Craw manufacturers' data? The answer to that is we would like to.
Do you want me to?
Sure, take it. Take it.
Yeah. So Energy Plus is a source for a lot of our algorithms, and there have been manufacturers that have provided chiller data to Energy Plus, and so that is a source of manufacturers' data. However, I think additional work can also be done for new equipment to have it fit the same kind of equations that are default for air and water-cooled chillers, and they could be added based on the performance data.
Mm-hmm. And we are working with any manufacturer would like to work with us on this. We'll get into that a little bit more in a moment, but yeah, if people want to work with us on this, we're thrilled to do it. And everything we do will be made public to we're working through the ASHRAE organization to try to publish everything we do so that others have it as well. I just had somebody correct. I made this chart. By the way, we were preparing these slides 10 minutes before broadcast. So that should say kilowatt hours right there, Henry. You would have picked that up if you would review that. So sorry, you're right. Whoever said that, that should be kilowatt hours. These are energy numbers, not kilowatt numbers. A question about, have you done CFD for in-rack cooling versus air handlers? The answer is sure. If you know, yeah. I mean, CFD can be used anywhere. You can use it in the rack. You can use it in the room. We did some modeling. Actually, Henry and I did some modeling on some optical rear door heat exchangers that he was using at MITRE, and we modeled inside the rack. So yes, this is true. Also, why did I say Boston was not so good for air-cooled chillers? Boston's not bad, but they tend to use them. You know, they're very popular in places where you have a little cooler climate. Boston gets pretty warm. So nothing unique to Boston, that's all, really. So here we're saving about 26%, Henry. I mean, this doesn't surprise you because this is kind of what we've seen before, you and I, right?
Mm-hmm.
But we've seen a lot more from the mechanical side, and we didn't get a chance to, well, in this case, it was an air-cooled chiller, so it was a box. There's not much you can do. But when these things are broken out, like we did a project recently where we had a cooling tower, we had a separate chiller, we had a cooling tower, we had a plate and frame heat exchanger, and we found the opportunity for energy savings there was higher because you could get sort of inside the box and make changes to specific components that allowed for optimization. And we gained a lot just from things like adding VFDs and so forth. So what this kind of modeling allows you to do is things like ROI. What did it cost to do those improvements I just made? Now, I did cold aisle containment. How much does cold aisle containment cost? I don't know exactly because I'm not in that business, but it's easy enough to find out. You get quotes on it, but at least now you know what the return is and how long it will take to return it. At $10,000 a year, the chances are you could return it in a few years, which is usually within the scope of reasonable for energy projects. And it also is the only way to know the total energy consumption prior to your build. Furthermore, the new ASHRAE spec is going to ask us as designers to look at that at 4 different points. What's it look like at 25? What's it look like at 50, 75, and 100? Not just 100. The historical method we've used is build for worst case loads. And what we found in the data center business is we're not seeing worst case loads. That's because the energy efficiency of the IT equipment itself has gotten better over time. They're running at lower voltages, they're using less power. Now that will eventually catch up, and then we'll get back on that same curve of increase again. But for now, I would argue, I don't know about your feeling on this, Henry, but I would argue that we probably have more cooling capacity than we need in many data centers.
Yes.
As a result, we're running way down on their efficiency curves, and you know what can be done about that.
Yeah, and the other factor that goes into that reduction is people moving to the cloud.
Right, but even in cloud case, I mean, I see it. What I find in the cloud case, Henry, is that when we work on those data centers, what happens is the customer will spec them for 10 kW per rack and then operate them at 3, right? So there's a bunch of unutilized capacity in those data centers as well because they've purchased capacity that they think they may need in the future but have never gotten to for the same reasons. And so many of my colos are frustrated because they're not getting as much load as they thought they were going to get, and therefore their cooling systems are inefficient. There's that problem too. So, okay, what are the optimal locations to install submetering to obtain real-time energy data for the cooling power and the IT energy for data centers? Question coming in, Henry. Optimal locations for installing submetering to obtain real-time energy data.
Yeah, I could talk about this one for a while, but this is more about a simulation than it is about operation.
Yeah.
However, operation, I think it's important to monitor temperature inlet and outlet temperatures of the racks at different heights. I think so you have rack level temperature data, and I think that working to add whatever you can to the building management system in terms of trending reports and things like that, that can better utilize what you've already got installed for monitoring and additional monitoring on pieces of equipment that aren't currently being monitored are the main general areas where I'd focus.
Now, in DCEP training, they talked about the popular idea is 3 inlets and 3 outlets on temperature for racks. Now, the point there becomes one of cost, because, you know, that's 6 temperature measurement devices per rack times the number of racks. Money can add up quick. So that gets tough. So what we tend to do is we'll sample. You know, we'll try to find racks that are in pretty tough shape and monitor those, put 3 and 3 on those. We'll put some on the good ones. We'll do a sample. The other point is, if you're going to measure power UPSs are a good place to go, right? That's the total, at least going into the IT equipment. But to get the efficiency of the equipment itself, or the UPS itself, you got to get on the other side of it to the equipment. You know, I would argue, Henry, I get your opinion on it. Measurement's tough. It's tough to do a good measurement. It takes time, it takes instrumentation, and it takes some effort.
Well, I mean, the ideal is to have monitored data running side by side with simulated data, and then you can tell when the operational data is differing from what the calibrated model was predicting, and that helps to troubleshoot and diagnose problems, to do preventative maintenance and other things that can result from being able to predict changes.
Question here also coming in. Let me just finish these up. And this relates to this slide here. We can do modeling services, and we did an announcement earlier in the year. It was supposed to be at Data Center World, but of course that got canceled due to our current health situation. But we as an organization can do servicing and creating modeling services. Henry has a lot of experience in this field. He was doing energy modeling long before he went into the data center business. He's also a member of TC99, as am I. He's also on the mechanical subcommittee of 90.4, and is leading the effort to put this all into mathematics. So the question came in, does this exist in CoolSim now? No, we're building it in, and there will be a release this year with some capability in it, but it won't be comprehensive. However, in the meantime, we have the code already done, and we can model it for you as a service. We just don't have the GUIs done and all the interface done and the reporting done. I showed you some of the reporting earlier, and I may go back to that now that we have Henry. He may want to walk through that reporting a little bit more. We've got most of it done for at least some basic functions like air-cooled chillers and a few other things, but there are many variations of mechanical cooling systems. By the way, I say many, but the quantity of variations is really not that large a number, you know. However, you need a way to capture them all and to get performance data for each of the components so that you can create the curves for them. If, however, you have currently a situation and you'd like us to do that work for you, we can do it as a service, and would be glad to do that. So a couple of points here about doing it for whom. HVAC manufacturers, for example, if there are any of you out there who are HVAC manufacturers and you'd like us to work with you on this, would be glad to do it. Often I see HVAC manufacturers who deliver tables and charts that show the performance of their equipment over an operating range. We have the ability to create those. So if you would like us to do any of that work for you, and Henry, I think you did some of this in your prior life, right? You did this kind of work.
Yes, extensively for many manufacturers and different types of equipment. The key point here is that the tables never seem to cover the point that you're actually operating at. And when you do curve fitting of the tables, then you're able to develop operating points that are arbitrary and more accurate. So the idea is to go from the table paradigm to a curve paradigm or to a software paradigm where you can put in your actual design conditions and get out the performance using empirical equations to plug into your design or to your energy calculations.
Mm-hmm. So we are able to do it and willing to do it for anyone who might like to have us do that for them. I am, however, going to, now that you're back, I'm going to go back to this energy report here, Henry, because it's new and interesting. This is a new report. For those of you who are CoolSim users, this looks very much like, you know, our existing report that we have for output, but it is got energy in it, more energy. Before we just had a very small entry here and not much, but now over here we have all these plots. Are there any here that you'd like to just spend a moment on, Henry, and walk through?
Go up one, that one there. Yep. Okay. I'm looking to do something as a function of dry bulb temperature, so that we could show.
Let me try this again. This was working earlier. Oh, so maybe that was it. I need active content. Let me go forward. This was working. Of course, when you were off the phone, this was working, and now that you're back, it's not. So let me just go back here and try this one. There we go. So that's operating load versus month. You wanted, let's look at operating power versus dry bulb.
Mm-hmm. Mm-hmm. Yeah, so this is an example of how the chiller's operating power varies as a function of the outdoor dry bulb, and there's 8,760 points plotted on this XY plot. The operating power has several functions or adjustments that are made as a function of outdoor dry bulb. The capacity of the chiller is adjusted as a function of outdoor dry bulb, as well as the power of the chiller. And the part load ratio varies as a function of outdoor temperature as well. So those are all combined in the graph that we see here, which shows that the chiller takes more power as it gets hotter out.
Yep. Yeah, the curve is something that's natural, and in the sense when you think about it, chillers are going to work harder and hotter dry bulb temperatures. Now, there's also here a cooling capacity factor. This is kind of an interesting plot here too. Do you want to spend a minute on this one?
Yes. So in this case, the capacity is varying as a function of the dry bulb temperature. Now that is this dry bulb temperature. Okay, that's the outdoor dry bulb temperature, and I'm not quite sure what this graph is actually.
Well, you've got chiller cooling capacity factor on the left. That's a ratio.
It is going. I mean, it's generally correct. I don't know about the bend in that curve, but the chiller capacity is highest at lower temperatures.
Yep.
Except that there's a minimum unloading capacity that takes place below a certain point. And then as the temperature goes up, the capacity of the chiller goes down. The chiller capacity is 1 at 95 degrees, which is the rating condition for chillers. And above that, it goes below 1.
We did have another question that came in, Henry, about where we got our weather data.
The weather data is typical meteorological year data, TMY3 data that we had processed to just extract the dry bulb and wet bulb and humidity ratio characteristics of the outdoor air.
Mm-hmm. Down here we have use per month. So this is monthly usage. I was going to look at daily usage as well, daily energy usage, days in the year.
Yeah, it's actually interesting to look at PUE and how just the difference in granularity affects the variation in PUE. So a monthly PUE is going to be almost constant, where an hourly PUE is going to have a lot more variation in it. And that's
So here's
seems
hourly PUE.
yeah.
This is part of the issue with PUE, and that you and I have talked about, is that, and I pointed out early on, is that PUE needs to be over a period of time, and you can see why.
And now if you go to the monthly, you'll see that this is 1.6. Yeah, monthly it doesn't get up to 1.6. It's very little variation when you average it on a month-by-month basis. The variation exists within the hours or the days. So
We had a question about does chill occur for water or for air? That was an air-cooled chiller, I believe, that we were looking at there.
yeah, in the models that we developed, we have air chillers and water chillers. And in the case of each one, we have different types of compressors. So for an air-cooled chiller, there will be a scroll, a screw, and a reciprocating. And for water-cooled chiller, there'd be those plus a centrifugal chiller as well. So the correlations take into account whether it's air or water, and also what type of compressor is being used in the chiller.
Mm-hmm. One of the questions coming in here, Henry, for you is on the mechanical side, we used a primary secondary pumping system, and the question becomes, do you see variable primary flows? Do you see VFDs being used on the primary side in data centers?
Well, I think that they can be used, but you have to maintain a minimum flow to make sure that there's, that the chillers will operate efficiently. But the minimum flow gives lots of room for variable speed pumping to have savings versus constant speed pumping for the primary loop. But you'd have to maintain a minimum flow.
It can be considerable as well as what we've found, right?
Yep.
Higher chiller efficiencies, we're seeing some very high, this is another question coming in, we're seeing higher chiller efficiencies. And so the general question to you is, do you see a need for cooling towers and plate frame heat exchangers anymore? Or are we all headed towards things like air-cooled chillers like the one we're seeing?
Yeah, that's a very interesting question. And, there has been a lot of change, and there is a lot more maintenance associated with cooling towers. The evaporative power of water, though, is a strong factor if you have adequate supply of water. So overall, the efficiency can be higher. But, as time goes on, the difference between those two seems to be getting lower and lower, as with cold temperature, high efficiency cold temperature heat pumps, for example.
Mm-hmm. Okay, so I think that pretty much summarizes it for today. I wanted to just go back and make sure that if there are any questions that they have been answered. So I'll just go back to my summary here, if I can get my computer to respond. There it goes. Yep. So we'd like to invite you to reach out to us if you're interested in having us do any of this kind of work for you. There's been a couple of questions about when can we get this capability inside the software. That's underway, ongoing. You should be able to see prototype versions of this popping out here, I hope, fairly soon. It's been difficult doing development lately, as you can imagine, for us all, but we're continuing to do it, and most of this work has been wrapped up, at least in a limited form of capability. Air-cooled chillers will come first. Those are fairly simple, but we already have the mathematics laid out for the rest of it. It's just an issue of getting it in there. In the meantime, we can do it for you. We're willing to do it for you. As I mentioned, the mathematics has been laid out. It works. We just haven't been able to get it into CoolSim itself. So as a service, we are more than willing to help anyone in our audience, including HVAC manufacturers who may want us to do some work for them in terms of modeling their components, or HVAC manufacturers that would like to work with us to make sure that their products are represented correctly in our models. We generally use, as Henry pointed out, algorithms coming from other sources, Department of Energy, for example, Energy Plus, DOE2, places like that. We work with the national laboratories, we do know them, and we work with them on approaches to these solutions and try to pick the best ones that meet it. But again, it's empirical and it's up to the equipment itself to, in terms of its behavior. So mapping its behavior can best be done with the cooperation of the manufacturer.
So yeah, I would just kind of summarize it that this custom modeling service is really intended for two different audiences. One is for someone who has a facility with a data center or multiple data centers, and their systems are such that they don't can fit into a conventional modeling situation, and they want to be able to model the system to either look at improvements or to be able to diagnose problems and or fine-tune the operations of the control systems. So in this circumstance, we go into an enterprise or a colo situation. We develop the models. We look at improving the systems, the controls, operations, or equipment replacements, and model what those potential savings would be. And then also, we can continue to use the models and compare the models to the monitored data for diagnostic purposes. In the case of the HVAC manufacturers, they usually have thermodynamic models that they use to come up with their calculations. We're not interested in reproducing those. We're interested in taking those, developing empirical equations for those, providing those to the manufacturer to include in software, or developing the software for them to that utilizes those equations and allows engineers or contractors to be able to select, size, and calculate the annual operating cost of their equipment in different situations with other cooling equipment and different IT situations. So the idea is ultimately to provide HVAC manufacturers, customers with a tool that they can use that takes them through the whole life cycle of sizing, selection, submittals, and specifications and operating costs and savings analysis. So we can, yeah.
Good. Well, all right. Well, I would like to close it out. We're at top of the hour. If any of you have any questions, you can send me a note. There's also a survey that will pop up at the end of our webinar here to ask you various questions about content and delivery. We would encourage you to fill that survey out, and there's also a place you can enter topics. If there's other topics in data center design optimization you would like us to have a look at, please let us know and we'll present one in the future. I want to thank Henry for participating in this with me today, and thank all of you for joining, and please stay healthy. Thank you, everyone.
Thanks, everybody.